This is the brief on analyzing non-recursive algorithms. If you've ever wanted to know exactly how fast a piece of code runs, say, something that checks if all the numbers in a list are unique, there's actually a rigorous 5-step method that gives you the final answer. So, first, you've got the setup. You have to identify the input size, which we just call n. Think of it like the length of an array. Then, and this is key, you choose the basic operation. That's the one thing that happens over and over again, the part that really does the most work, like a comparison or an assignment. Okay, second, once you've got that, it's calculation time. You need to count exactly how many times that basic operation runs, which usually means looking at the loops in the code. This count gives you the total cost function, written as T of n, which is just a way of expressing the total operations based on that input size, n. And finally, it's all about standardization. You simplify that function using standard forms, like big O, big omega, or big theta. This is where you drop all the little constants and smaller terms. Why? Because what we really want to know is how the algorithm holds up when n gets huge. That's what reveals its true efficiency at scale. Following this 5-step sequence provides the definitive mathematical framework for understanding and communicating any non-recursive algorithm's performance. This is the brief on analyzing the efficiency of algorithms. So we're talking about a structured 5-step method for looking at non-recursive algorithms. And this is really key, because it helps us understand a program's true performance when you're tackling fundamental problems. Like finding the maximum element in an array, or checking if every single item is unique. First up, you've got to lay the groundwork. That means identifying the problem size, what we call n, which is usually just the length of the array. Then you choose the basic operation. This is the single action, like a comparison, that's going to happen the most. Second, we get into the measurement phase. You need to count exactly how many times that one basic operation runs. After that, you express this total as a function of the input size, n, which gives you what's called the total cost function. And finally, the most crucial step. You simplify everything using asymptotic notation. This is where you drop all the constants and lower order terms to see what really matters. We're talking big O notation here. It gives you the definitive answer on how well your algorithm is actually going to scale. Mastering this 5-step approach is how we formally measure and guarantee the optimal performance of any non-recursive code.
The slide shows an example of finding whether the elements in the array are unique or not. An array is given with elements like 4, 8, 7, 1, 9, and 10, whereas the indices are given as 0, 1, 2, 3, 4, and 5. The idea behind finding the array elements are distinct or not is by comparing the first element with the remaining n minus 1 elements. If there is no match, then the process will be continued. Okay, that's what it is given. Like first, we are comparing a of 0 to a of 1 until a of 5. If there is no match, we have to select the second element, that is 8. 8 will be compared with the remaining elements. 8 will be compared with the 7, and if there is no match, it has to be compared with 1. It has to be compared with the 9 and with the 10. Since still, if there is no match, then the process will be continued in such a way. We have to start from a of 2 till the remaining elements. So keeping this as the idea, so we are writing the outer loop. The outer loop is starting from a of 0, and it is over by a of 4, that is n minus 1. Here, the starting index is 0 and the end index is 5, so it is n minus 1. So the outer array is given from I equal to 0 to n minus 1. The inner loop starts from 1 and it ends at 5. So we are writing that relation, the second loop, that j is starting from I plus 1 and it is less than n. Why it is I plus 1? If you see the relation of a of I, when a of I, that is the outer loop, when a of a is getting started from 0, the inner loop will start from the second element of it. When a on the inner loop is a of 1, then the loop should be start to do the comparison from a of 2. If the inner loop value is a of 2, then it has to be from a of 3. So when I is equal to 1, j will start from I plus 1. Then we do the basic operation of comparing the elements of a of I and a of j. If there is a match, we say return 0, that is the elements are not distinct. Else, we call that as distinct. Let us see the analysis. The function t of n is given in such a way. There are two outer loops. So there are two loops. The first one is the outer loop I equal to 0 to n minus 1. The second is the inner loop. J starts from I plus 1 to n. And the basic operation is a comparison. For every such iteration, it is happening once. That is written here. Then we first try to solve the inner loop. So applying the condition of upper limit minus lower limit, we get the value like n minus 1, n minus I. Then we apply the condition I equal to 0 to n minus 1 to the determined value of n minus I. So we get the format of n plus n minus 1 plus n minus 2. It goes up to n. So if you observe it, it is a pattern of sum of n numbers, which is written as n into n plus 1 by 2. Whereas in the case of asymptotic notation, it can be written as big O of n square or big theta of n square or omega of n square.